Alright, hello, and welcome to part 5 of the mini chemical kinetics series. In this video, we are going to be doing some of the textbook problems from Pearson Education's The Principles of Chemistry and Molecular Approach textbook. So that's where I am getting these questions. The first one we'll look at is from chapter 13. It's question 20. It's saying, consider the data showing the initial rate of a reaction at several different concentrations of A. And then it is asking for us to determine the order of the reaction, then writing a rate law for the reaction, including the value of the rate constant K. So we have quite a few little pieces of the puzzle that we need to solve. The first thing that I'm going to do is write an outline of what this rate law should look like. You know that rate is going to equal K, our rate constant, times the concentration of A raised to the n power, or to the reaction order. The easiest way that we can go about this is to solve for n first. And that will allow us to plug in any row of this equation and then solve for K. So we'll go ahead and do that first. And if you recall from the last video, I went into depth about how we can find a reaction order if it's not apparent just by looking at the data. In this case, we have scientific notation, and these numbers don't really go into each other very nicely, so we can use this equation. Alright, so we'll go ahead and use that equation. I'm going to switch. Alright, we can pick any two rows in this equation. I'm going to go ahead and just use the first two. So we'll go ahead and we'll use this equation. I'm going to just start plugging in values. Rate 2 would be 8.75 times 10 to the negative 4th molarity per second divided by the 3.89. That is going to be equal to K, which we don't know yet, times A. The concentration of A for the second experiment, that is 0.18 molarity, raised to the n power, that is what we're solving for, divided by K times 0.12 molarity raised to the n power. Now I'm just going to cancel out what appears in both the numerator and the denominator. That would be the molarity per second right here. Our K, or our rate constant, will cancel out, and the molarity unit will cancel out. Okay, now we'll just simplify. This left side will simplify to be 2.25. And if I set that equal to this fraction, comes out to be 1.5, and we're raising that to the n power. If we cannot easily determine or see what the order of the reaction is, we can use the logarithms. So I'm going to take the log of both sides. On this right side of the equation, we have log of 1.5 raised to the n power. And just as a reminder, whenever you have a log of something raised to an exponent, that will simplify to the exponent times the log of x. I'm going to go ahead and rewrite this using that property. So then we'll have n times the log of 1.5. Now I can isolate n by dividing both sides by the log of 1.5. And if we go ahead and do that math, we find that we get approximately 2, which means that we have a second order reaction. Next, we can find K. I'm going to erase this part down here, just say second order, and I'll find K over here. We now know that our rate looks like rate equals the rate constant times the concentration of A raised to the second power. Since we haven't used that third row yet, I think I'll go ahead and just plug that row into this equation, and then we'll solve for K. Now this exponent 2, is going to distribute to both the number and the unit. If I go ahead and just rewrite this, get K times 0.28 squared comes out to be 0.078, and then we would have molarity squared. We want to solve for K, so I am going to isolate that variable by dividing both sides by the 0.078 molarity squared. Doing so gives me this. And when I simplify that, the number value that I get for K is 0.027. My units, if we look at this, one of those molarities in the denominator cancels out with the 1 molarity in the numerator, and I am left with units of inverse molarity times inverse seconds. Now that might not be what you remember from the example we did in the last video. We had units for K in inverse seconds. To make sure that our rate always is in units, K units, or the rate constant units, will change depending on the reaction order. As you will go on to see, if you have a reaction order of 0, your units will be molarity times inverse seconds. If you have a reaction order of 1, or a first order reaction, you will have units of inverse seconds. And if you have a second order reaction, then you will have units of inverse molarity times inverse seconds, as we just saw. Now, if you have any fractions or higher order numbers, then your K will change. In the next example, we will see how that happens. But K will fluctuate. The units for K do fluctuate depending on the order of the reaction. So don't freak out if you have different units than what you might have seen. It depends on that order. We were in second order, so this makes sense. So putting it all together, the rate law for this reaction would be, I'll write it in the bottom left, rate equals 0.027 inverse molarity times inverse seconds times the concentration of A squared. All right, in this next problem, we are looking at the reaction between methyl chloride and chlorine gas. It is asking for us to write a reaction rate law and calculate what the value of the rate constant K is, and now it's also asking for the overall order of the reaction. And here we do have 2 reactants, so each reactant has its own specific order, or reaction order. Our kind of outline for what this rate law would look like is rate equals the rate constant times the methyl chloride raised to its own personal reaction order times the chlorine gas also raised to its own personal reaction order. The overall order is going to just be the sum of those 2 reaction orders, so it'll be N plus M. Alright, now when we deal with reactions where we have 2 reactants, we have to go about determining the reaction order very carefully. We want to focus on one reactant at a time, and we want to pick, these are each experiments or trials. We want to pick 2 trials for the reactant that we are looking at. In this case, we'll look at the methyl chloride first, and so we want to look at the methyl chloride column and pick 2 rows where the concentration is changing, but the concentration of the chlorine gas must remain constant. So here, the only 2 experiments that I can pick are these first 2. I'm going to star them because the chlorine gas is remaining constant, but the methyl chloride is changing. So if I am looking at trying to determine what the reaction order of the methyl chloride gas is, I'm going to look at experiments 1 and 2. And we'll solve for the reaction order like we just did. If you would like to pause the video here, see if you can try to determine what the reaction order is. I would suggest that just to see if you're following along, and then press play to see how it is solved. Alright, so we're going to use that outline, that equation, putting it over here. So we're still using that equation with the ratios. I'm going to go ahead and plug in my rates for the first 2 experiments. That is 0.029 molarity per second divided by 0.014 molarity per second, and then I will look at the right side of the equation and plug in values there. I'm going to go ahead and cancel out terms that appear in the numerator and the denominator. And now I'm going to go ahead and simplify both sides of the equation. The left side simplifies to about 2, and then the right side also simplifies to 2 raised to the n power. Now, if you can't see this, we could do the logs. However, 2 equals 2 when 2 is raised to the first power. If you raise something to the first power, it equals the identity of the base unit, in this case 2. So we know n is going to equal 1. This is a first order reactant. And that is all we have to do for this part. Next, we'll look at the chlorine gas. In this case, I'm going to erase those stars. I want to look at chlorine gas and pick 2 experiments where the concentration of chlorine is changing while the concentration of the methyl chloride remains constant. Looking at that, I can see that experiments 2 and 3 would satisfy that requirement. Methyl chloride's concentration is not changing, but chlorine's is, so I can use experiments 2 and 3 in this case. I'm going to do the same thing where I use my rate equation and I just plug in values. Alright, we'll go ahead, cross out like terms, and now we'll simplify both sides of the equation. The left side comes out to be 1.4, and we'll set that equal to, again, 2 raised to the m power. Now this isn't clear what we could raise to get 1.4, so I'm going to go ahead and take the logs of both sides. The right side of the equation does simplify out to be m times the log of 2. I can then solve for m by dividing both sides of the equation by the log of 2. I'm going to go ahead go over here to do that. And when I plug this into a calculator, I get 0.48, which is approximately 0.5 or 1/2. Now this is okay. This is an okay order. It's not one of the most common orders that we see, but having a reactant with a order of 1/2 is totally satisfactory. So we don't have to worry. Now my overall order would just be the sum of each of these n and m values. So it'd be 1 plus 0.5. That gives me an overall order of 1.5. I'm going to go ahead and update what my rate law looks like. My rate law at the moment looks like the rate constant times the methyl chloride raised to the first power times the chlorine gas raised to the 1/2 power. Now I'm going to go ahead and erase what I have down here to make room so that we can solve for the rate constant. All right, so I went ahead and erased everything. I also moved, I wrote that the overall order equals 1.5. The last thing that we have to do to answer this question is solve for K. So that is the last thing that we got to do. Since we now know what the reaction orders are, we can pick any experiment and plug in the values, the corresponding rate value and the corresponding concentration values of our reactants, and then solve for K. Since we haven't used this fourth row, I'm going to go ahead and just use that. We will get the same answer no matter what. But since we haven't used it, I thought we might as well just go ahead and do that. I'm going to first rearrange this equation to solve for K, just to isolate that. To do so, I would just divide both sides by the concentrations of our reactants. Get a new equation that looks like this. You don't want to forget that exponent. It is common to accidentally forget that, but we really want to be careful and make sure that we include that. Next, I'm just going to plug in values. Our rate is 0.115 molarity per second divided by the concentration of methyl chloride times the concentration of the chlorine gas raised to the 1/2 power. I'm going to go ahead and simplify that denominator. That comes out to be 0.0894 molarity to the 1.5 power. Remember, when we multiply exponents together, we end up just adding them. Okay, and now if I go ahead and do that division, we get 1.29. For our units, when we divide units, in this case we're dividing m to the first power divided by m to the 1.5 power, we subtract. We subtract the denominator. Let me go ahead and do. We subtract the exponents. Doing so gives us an answer of 1.29 molarity to the negative 0.5 times inverse seconds. You could also write this value as 1.29 divided by molarity to the 1/2 times seconds, and then you don't have negative numbers. But if you wanted to write them all in one row, like I did here, you could do that as well. You just have to include the negative number. Now, if we go ahead and write our final rate law, including the K value and including the proper reaction orders, we would have an answer of 1.29 molarity to the negative 0.5 times inverse seconds times the concentration of methyl chloride to the first power times the concentration of the chlorine gas raised to the 1/2 power. And that is how we would do these problems. I hope this has helped you. I hope you have a better understanding of questions like this. If you have any questions, please leave a comment. And thank you for watching.